electron configurations. What do you think those words mean together?
Location. Way they're built up.
The configuration of electrons.
Yeah, the configuration of electron. Thank you. That's like using the word in the definition.
Spread it out.
All right, how else? What's another word for configuration? Arrangement. Design. Yep. Location would have worked too. All of those things would work. Okay, so electron configuration is the arrangement of electrons in an atom. Okay, the arrangement of electrons in an atom. In our chapter 3 when we talked, or chapter 2 when we talked about atomic theory, we went through a couple different theories of where our electrons located. And so now we're really going to get into what we know today about electron placement, what we know today about electron location, all of that kind of stuff, okay? There are a lot of ways that electrons can configure themselves in an atom, but we're going to start with the most basic version of that, called a ground state electron configuration, okay? So a ground state electron configuration means that atoms are in their lowest energy arrangements, right? Similar to teenagers, they want to have the lowest energy output all the time, right? Agreed? I know. I'm right. Don't say I'm wrong. I'm right, okay? They want the lowest energy level possible. So when you have electrons that are excited, right, that's the alternative to ground state. You have excited state electrons. When you have excited state electrons and they fall out of the excited state, that's when you have the emission of light. Okay, so it's constantly happening, right? Electrons are excited state, they go back to ground state, they go excited state again. That happens, and that causes the emission of light. And so we're going to go with ground state electron configurations. That's their lowest possible energy levels. It's like when everything is where it's supposed to be, right? It's just nice and calm. Everything's where it's supposed to be. And we're going to learn how to determine what is the ground state electron configuration for any element, any ion. We can do it for either elements or ions, okay? Before we even get into that, remind me, what is an ion? Say it. Everybody should know it. What is it? A charged atom. Different number of protons and electrons. Anything that has a charge. Good. And what is a negatively charged ion called? An anion. And what's a positively charged ion? A positively charged is called a cation. Very good. Very good. Okay. All right, so we'll be able to determine ground state electron configurations for both neutral elements and ions, okay? Because we're really talking about electron configuration. So when an element has a charge, it's not a different number of protons, it's a different number of electrons, right? Because what would happen if I would alter the number of protons? It would be a different element. Yep, good. Okay, so this is a representation of a different, or a representation of what's called orbitals. So I'm going to take a little step back here from our slides. We're going to have to write a few extra things down that I don't have on the slides, but I think that are really important, okay? The first thing that I want you to write down outside of your slides is a couple definitions here. Okay, the first definition I want you to write down is called an electron orbital. An electron orbital. Okay, and I'm not even going to give you the book definition because I don't know what it is, but I'm going to give you what a basic definition is, okay? An electron orbital is basically, I don't know, I'm going to say a pocket where electrons are located, okay? There are pockets of electrons that surround the nucleus, and different versions or different types of electron orbitals have different shapes. And so we're going to explore what do those shapes look like, how many electrons can fit in each pocket, all that kind of stuff. But we got to start with basics. So each electron orbital can hold 2 electrons. Can hold 2 electrons. That's really, really important. Each individual orbital can hold 2 electrons. Now, there are multiple versions of multiple shapes of orbitals that surround the nucleus. So really, if you can start envisioning manganese that has to have 25 electrons, there's got to be a lot of different orbitals around that nucleus, right? Because we've got to fit 25 electrons around there. And so we've got different layers that we put on these atoms, right? Our first shell of electrons can hold 2 electrons. The first shell of orbitals can hold 2 electrons. Then the next shell can hold 8. Then the next shell can hold 8. And then the next shell can hold more than that. And so they kind of expand and they get different shapes as we go. So electron orbitals, it's a pocket and it can hold 2. All right, there are 4 types of electron orbitals, okay? There are 4 types of electron orbitals, okay? And they have letters that are associated with them. They are S, P, D, and F orbitals. S, P, D, and F, okay? So we've got these categories of orbitals. Now, we are able to translate orbital shapes, orbital sizes, orbital locations to the periodic table, right? It's almost like a pattern that we see on the periodic table that happens to mimic the pattern of the electron orbitals. So I'm going to introduce you to the orbitals first, and then I'm going to show you how that pattern reflects on the periodic table. Okay, I want to say it's coincidental, but it's not, right? But it just works out to show us how these orbitals are arranged, okay? Now, for each type of orbital, there is only one version of an s orbital. Oh, can't spell. One version of an s orbital, which means it can hold a total of 2 electrons, right? Because each orbital can hold 2, and the s orbital, there's only one type of that orbital. Okay, the p orbitals, there are 3 versions of that orbital. That means it can hold a total of 6, right? The p orbital itself can hold 6. Are we understanding how that works? Right? 3 versions, so that 2 times 3 is 6, right? Remember we understand where that's coming from? Let me walk it back a little bit further. When I say versions, I mean like ways that it can orient itself around the nucleus, okay? So I'll show you a picture of it here pretty soon so we can bring it all together. But the d orbitals have 5 versions, which means it can hold a total of how many? 10. And then the f orbital has 7 versions, which means it can hold a total of 14 electrons. Okay, so now that we've got an idea of what an orbital is, how they kind of work, I want to skip forward just a tiny bit in your slides, and I want to look at the shapes of these orbitals. Okay, what three-dimensional shape do they really represent? So we're going to skip up to that here in your slides. So I want you to look at, I didn't actually put up the shape of the s orbital because it's a sphere. Okay, so it's not that exciting. But this is all 3 versions of the p orbitals. Okay, they make 3 different orientations around the nucleus, right? They call it an x-axis, y-axis, and z-axis orbitals. But we have 3 different versions. And if we put them all together, you would see those 6 electron pockets right around there. So this is one version of the orbital. There's its 2 electrons. Here's one version of the orbital, 2 electrons. One version, 2 electrons. So when they all fit around the nucleus, they orient themselves so that they all have room, if that makes sense, right? They all have equal spacing around that nucleus. This is an image of the electron cloud, okay? It's essentially that this is all representing those 6 electrons, okay? Oh, no, these 2 electrons, 2px. So this is an electron cloud picture of a 2px orbital, which means electrons don't stay in one spot, right? They bounce around. So it's not that we have this many electrons in the orbital. There's only one here, one here. But this is how much space they have to roam. Does that kind of make sense? Okay, so all those dots are not individual electrons. They are images of where the electron was located at a certain point in time. Okay, so this gives us an area of how big that orbital is and kind of the shape of that orbital, right? It's got that much room to kind of roam there. So really there would be this one and 2 other orbitals around that nucleus. Okay, so the p orbital's got 3 versions, which gives us a total of 6. The next one has d orbitals, okay? 1, 2, 3, 4, 5 versions of that orbital. These shapes get much more complex, okay? There are 4 spots there, but they only hold 2 electrons, so that the electron's either there or there in that orbital. The electron's either there or there in that orbital, okay? So the d orbitals get a little bit more complex, and then the f orbitals get even more complex than that, okay? The shapes that they take on, okay? Yeah, it's kind of funky, right? And there's a lot of space there. But do you see how with these orbitals, they have to kind of be skinny, and then they can get a little bit more space? Why do you think they have to be skinny toward the center? There's already other orbitals there, right? You've got p orbitals that are taking up space there. You've got d orbitals that are taking up space, right? And so even these, they're kind of removed from the origin a little bit, right? That's because you have to have space there for those d and p orbitals.
Do any of them orbit into the other, orbit in this?
No, so the only way that an electron would jump from one type of orbital to another would be if it was an excited state electron. So if enough energy gets put in, electrons will jump, right? And they'll negate their orbital to go to the next one. Okay? Yeah, go ahead.
Is there a difference in size of orbitals? Like, is the S orbital smaller than the
Uh-huh.
S orbitals?
Yeah, a little bit. The s orbital is just a sphere that sits right around the nucleus, and then everything else gets piled on top of that. Then when we get to, let's say we get to the end of let's go with neon. Neon has a full octet, right? So when I want to add another electron to neon, it has to be added a whole nother shell. So we start over with an s orbital. Okay, that's what we're going to talk about next. How do the electrons go in? Okay, once we have a full octet, we don't have any more room for electrons in those orbitals. We have to add another shell. So a whole nother s orbital kind of encompasses that whole thing, and then we start over again, right? So it gets bigger and bigger and bigger. Okay?
That's weird.
It is weird. But what's weirder, I think, is how it's mimicked on the periodic table. Okay, so let's walk through that. We talked about s, p, d, and f orbitals. And so now I'm going to show you how those are represented on the periodic table in what's called blocks. Okay? These two groups of elements right here are called s block elements. Okay? S block. How many groups are there? 2. How many electrons can the s orbitals hold? 2. You see where I'm going? Okay, the p block of elements are right here. How many groups is this?
No, 6.
6. And how many electrons can the p orbitals hold?
6.
No,
6. 6,
Oh, you're
right? 3 versions times 2 electrons each
Right,
is
6
is 6 electrons. Okay, the d block of elements is this one in the middle right here. The transition elements are in the d. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just like we said, 10 electrons can be held. And then the lanthanides and the actinides down here, those are the f block elements. And how many would you guess? Right here. 14, right? So that pattern is mimicked on the periodic table. And it gives us an idea about where the last electron for that element is located. Okay? So let's talk through this real quick here with hydrogen. Hydrogen has how many electrons? Neutral hydrogen has how many electrons? 1. Okay. So the first electron to go in any element, okay, and hydrogen's only electron, gets put into an s orbital. Okay? It gets put into an s orbital. The second electron that goes in is also put in the s orbital, okay? Helium would sit really over here, okay? After that, we have to make a new shell, okay? The s orbitals, the first shell of any atom can only hold 2 electrons. After that, we get to our octet rule, okay? So the first 2 electrons that go in are in s orbitals. Then we start over again with another s orbital called the 2s orbital. 2s2. Then we fill another electron and go to the p orbitals. Okay, so once we fill up those s orbitals, we're going to go from there. All right, I think I'm not making sense right now, so let me try it again. I want you to look at an electron configuration really quick, and we can get an idea of what we're supposed to be looking at here. Let's look at the electron configuration for boron. I'm going to write it out, and we're going to see if we can see a pattern with it. Okay, so the finished electron configuration for boron is 1s2, 2s2, 2p1. Okay, that's the finished electron configuration for boron, and I want to see if you can figure out how we got there. Okay, boron's last electron is electron number 5. Would we agree with that? Okay, so its first 2 electrons have to go into the s orbitals. Okay, the 1s orbitals, the inner shell, 1s. Then we had to add a new shell called 2s. How many electrons can they hold? 2, right? After that orbital is full, it has to move on to the 2p orbitals, right? And one of boron's electrons sits in the 2p orbital. So we follow the pattern on the periodic table to figure out where do our electrons go, right? They go into the s orbitals until they're full. And I don't have anywhere else to go here, so I have to drop down. 2s. Then I move over. 2p. What do you think would come next? 3s. Then 3p. Do you see the pattern as to how the electrons go in? Right? We're going to follow that pattern. Yeah, go ahead.
And then the p can hold 5.
Start with 1s, and then how many electrons can fit in that 1s orbital? 2. Is there any such thing as 1p? No. So I move on, right? I've finished this row. I move on to the next one. So I'm going to go 2s. How many? 2, right? So those are done. I'm working my way over here. This is 2p, and I have got all 6 of those, right? Because I'm trying to work my way to cobalt, right? I'm going to follow right along the periodic table until I can get to cobalt. Okay, so after 2p, where do I go? 3s2. Okay, so that's done. Now I'm going to work my way over here, which would be still 3. So 1, 2, 3. Okay, so 3p6. Good. So that's done. I'm going to drop down here. What would this be? 4s2. Okay, so now here's where we came to that tricky part where I said this. You would think this is 4d, but really the whole d orbitals are like shifted, so they should be up 1. So this is 3d, right? So the d orbitals start with 3, not 4. So this is 3d, and then we just count. 1, 2, 3, 4, 5, 6, 7. 3d7. And that's our final configuration for cobalt.
If you were to add all the exponents together, then you would get 27.
Bingo. I was just going to say that. Okay? The way you check your answer to figure out did you do it right or not, you add up all of those superscripts, and they should add up to the atomic number, right? The number of electrons that we put in. Okay, so let's try it. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, 18, 20, 27, right? We did it. Okay, yes, Keva.
If you have like one of the green ones on the bottom.
Yeah, it gets even more gross. Okay, this is 4F, 5F, even though they fit right here.
Wait.
Yeah, I know. 4F, 5F.
So that's nice.
The fourth is 3.
Yeah, I know. Even though it would fit right here, 3, 4. It would go 6S, 4F, 5D.
Really?
Yeah, I know. But I don't ever give you problems that deep. Yeah.
Really?
But that's how it would work. Yeah, I don't usually. Yeah. If I was going to go with plutonium, is that PT? What's PT? Yeah, platinum, sorry. If I was going to go platinum, I would go 6S, 4F14, 5D, 1, 2, 3, 4, 5, 6, 7, 8. That's what it would look like.
I know what that is.
Okay, let's try it again. Let's do just the ending for that one. I want to see what that looks like. Let's say I was going to look at platinum. I want to start it again. I'm going to ignore the whole beginning part, and I'm going to start right here. Okay? So I would go 6S2. Now the lanthanides and the actinides fit in right there, right? That's where they go on the periodic table. So I said this one starts with 4F and 5F. So I'm going to go 4F, and it can hold 14. The next thing right here, if this is 3D, 4D, this has to be 5D. So I would go 5D, 1, 2, 3, 4, 5, 6, 7, 8. All right, that's how it fits in. Again, I'm not going to give you ones down here, but that's how it fits together. Okay, so those F orbitals become available in the 4th energy level. We still are always going to fill it in the order of the periodic table. Okay, so you're just going to follow that along. Yeah.
Is there like a way to simplify or write this simple?
Yes, there is. It's called an abbreviated electron configuration. I'll show you that here in a second. Yep. Yeah,
I have a
basic.
question. So you said we can't have a 1p.
Yeah, right.
Why is that?
The first energy level of the atoms only holds 2 electrons, right? That's why hydrogen never needs a full octet, right? Because it only has 1 electron to give. So that's just the first energy level only has 2 spots. And then that next one opens up to we have the s orbitals and the p orbitals. So that's why we talk about an octet, because 2 from the s orbital plus 6 from the p orbitals is 8. And so that's where octet comes from, right? We want, in order for our octet to be full, we want our s and our p orbitals full. Mm-hmm. Yep. Okay.
So with each new shell, it's like a level out.
That's right. That's right.
So a new shell starts with S.
Yes,
So
that's
every
right.
time, so like we would have had 6 shells.
That's right.
Not 4 shells or 5 shells.
Nope.
6 shells.
Yep.
So then the 4 and the 5 represent energy level, or what?
It's in that 6 shell. It's just they become available at that energy level. Yeah.
Can you use another example?
Yep. Yep. Let's try an example for. Let's do chlorine. Cl. All right, I think I gave you a slide with just some room for practice electron configurations. You can check if I gave you a blank slide there. Did I do that?
Yeah.
Okay, so now you've got some room for practice electron configuration. So let's try that. Let's do chlorine. Okay, so I'm going to start with what? What do I start with? 1s, and an s orbital can hold 2 electrons. Then I have to jump down, right? There's no 1p, so I'm going to jump down here. The next one is 2s, and that can hold 2. Then I'll work my way across to this block right here, which is called what? The 2p. 2p. And that can hold 6, right? If you can't remember how many a block can hold, just count. 1, 2, 3, 4, 5, 6, right? After that, I'm going to jump down to sodium. Now I'm at 3s, and it can hold 1, 2. Then I'm going to move over to chlorine, which is 3p, what? 5. 1, 2, 3, 4, 5. Okay, so that is a finished electron configuration. Okay. ZR, zirconium, number 40. So this is going to be kind of a long one, and then I'm going to show you how to abbreviate it. All right, I'm going to let you try this one on your own, and we'll see if we match, okay? Follow along the periodic table. Remember that shift of the d orbitals. Guys, you getting started? Okay. I'm going to give you a head start. Uh-huh. After I go from 3p?
So I'm at 3s2, I'm at 3p now. So do I write 3p?
Well, are all of those full in order to get to zirconium?
Yeah.
Yeah, so then it's got to be 3p6. Yep. And if you can't remember, then just count. 1, 2, 3, 4, 5, 6.
Okay.
Right?
If you memorize, because it's all like a pattern. 1, this is 4, that's 2.
Yeah.
2s, 2s.
Mm-hmm.
Memorize the whole series.
3d10. Yep.
4,
That was too long. There's so much
Over.
I need the D's.
When we look at electron configurations, we're going to assume most of the time that our beginning stuff does all look the same. But let's walk through it since we're still learning here. 1s2, 2s2, 2p6. We jump down again, 3s2, 3p6. Here's where it gets a little bit funnier, right? 4s2. So we're at potassium right now. 4s2. Now we start on the d orbitals, which we said are 3d, right? Again, I don't make the rules, I just teach you the rules. 3d10. Then we jump back to 4p, how many? 6. Then we're going to jump down, right? We're done with the fourth. 5s2, 4d2. I'm going to stop. So if I wanted to add up all of those, what should they add up to? They should add up to 40. Okay, that should be my goal, is that they add up to that particular atomic number.
So the middle ones are always, the top ones are always, these are all start at 3.
Yeah, 3D, 4D, 5D, 6D.
So we skipped it to 4 and then come back to 3.
Yeah. Yes. Yep. All right, now I'm going to show you how to write what's called an abbreviated electron configuration. So that means we're going to be able to take out a bunch of that stuff at the front. Okay, an abbreviated electron configuration. You will have to know how to do both, right? Sometimes I will ask for the full, and sometimes I will ask for the abbreviated. But we can abbreviate it with what's called a noble gas. And we know what noble gases are, don't we? Where are the noble gases located? What group number? Group 8, right? Group 8 or 18. Noble gases, why do you think we would use noble gases to help us show electron configurations? Why would they be important? Yeah.
They have a full shell.
Bingo. They have a full shell, right? One of their energy levels is totally full. Okay, so we only use noble gases to abbreviate these. Sometimes you'll hear this called noble gas configuration, right? This is the same. I call it abbreviated electron configuration, but noble gas electron configuration means the same, okay? So let's say that I want to find the electron configuration of calcium. Let's find the full electron configuration for calcium. Okay, let's do this one together. Full configuration for calcium would be 1s2, 2s2, 2p6, 3s2, 3p6, and then what? 4s2, right? Okay, if I wanted to add them up, they should add up to 20. 2, 4, 10, 12, 18, 20. So that means my electron configuration looks right. We at least got the right number of electrons. Now, I want you to tell me what is the noble gas in the energy level above calcium. So I want you to go to calcium and work backwards until you get to a noble gas. What is it? Argon. Okay. Now, what is the configuration for argon? Argon is 1s2, 2s2, 2p6, 3s2, 3p6, isn't it? And so don't those look identical up until that point? So the abbreviated electron configuration is going to look like this. It is the configuration for argon plus whatever's left over. So 4s2. Okay, you put argon in brackets, and then you add on whatever else you need to get to your final answer, right? So we're going to say calcium's electron configuration is identical to argon plus 4s2. Okay? Yeah, Luke.
How do you know which one's noble gas?
It's always the last group. Anything in group 8. So helium, neon, argon, krypton, xenon, those ones. Okay? You cannot make an abbreviation with itself. So if I said find the abbreviated configuration for argon, you can't just say argon. Right? That's like saying the definition. That's like saying the word in the definition, right? So if I wanted the electron configuration abbreviated for argon, I would have to go neon plus 3s2, 3p6. Okay, does that kind of make sense? Okay. All right, very good. Let's try, I've got a couple of practice for you there on the next slide. Give the abbreviated electron configuration for iron, strontium, and tellurium. Why don't you try those 3? Okay, I'm going to give you a head start here, and then that'll be it. Good.